Alright, Physics 12. This is the continuation from the equilibrium video. So, as mentioned, we really only, we were only able to get through one problem. If you were okay with that, that's fine. But if you're watching this video, you want to see full solutions and explanations to the other problems that are there in the slides. So we'll just kind of go through those together. So this was sample problem number 2. So in this one, you have an 18 kilogram sign that hangs symmetrically, so obviously evenly, from a 7.8 kilogram uniform rod that is 1.3 meters long and is attached to a wall. Okay, a cable that makes a 35-degree angle with the rod helps to support the rod at its end as shown. And we're being asked two things. One, what's the tension in the cable? And two, or B, I guess, what force is the wall exerting on the rod? Okay, so let's start with that one. All right, so again, if we take a look at what we've got going on here, right, a simpler drawing. All right, so this is kind of our sign on the rod there. What we have is that this is a 35-degree angle with the cable. You have a force of tension pulling up this way. You have two separate forces acting here. Right now, what's nice about this is the sign is hanging symmetrically, which means that the center of gravity of the sign, right, the center mass of the sign is also the center mass of the rod. Okay, so if we kind of get rid of the actual diagram here, you actually have two specific forces, or weights, I guess, happening here. One for the rod, all right, so force of gravity for the rod, and then from that same one, a larger force of gravity for the sign. And the reason this is larger is because the sign weighs more, right? Because we have that the mass of the sign is 18 kilograms, whereas the mass of the rod is only 7.8 kilograms, right? So this one will have a larger value. Now, the other force at play here is kind of mentioned in part B, is that what's the force being exerted by the wall, right, onto this sign? And the thing is that there's kind of, again, you got to think of this in two dimensions, right? You've got a force that could be acting this way in the x direction, right? But you also have a force that can be acting here, right? So I'll actually specify that. So this is the force of the wall in the x, and this is the force of the wall in the y. And we can't assume at this point that those are equal forces, right? So like we can find overall the force of the wall after we get it in components, and then kind of combine them together using our wonderful little Pythagorean theorem, right? And that'll give us the entire force of the wall, okay? That it's exerting on the sign. Okay, so these are kind of, this is our diagram, this is what's happening, right? So Ft, that's the force of the tension in the cable. Fgr, that's our weight of the rod. Fgs, that's our weight of the sign, right? This is the force of the wall in the y direction. This is the force of the wall in the x direction. Now, we are asked in this first part of the question, what's the force of tension? Okay, so again, what you might start thinking about, right, is options. Okay, so if it's an equilibrium, right, so the sign's not, falling down or moving anywhere. So we're thinking, all right, well, the force of tension seems to be in, obviously in two dimensions, right? So it's kind of got an x and a y component. So if we started by thinking, okay, well, let's do all the forces in the x, you'd be like, okay, well, I don't know this, and I don't know this, so I can't get the actual component. Okay, so that's not helpful. What if we tried to do the sum of the forces in the y? Okay, don't know this. I can get these, that's no problem. Because I don't know this, I couldn't get the actual y component of it. Okay, so what's left? Let's try the torque, right? So, okay, so in that case, let's start with that the sum of our torques need to be equal to 0. All right, well, if we're going to talk about sum of torques, we need to identify a pivot point. Once again, if we can identify this as our pivot point, these two things just become 0. And these are the things that we'd want to be 0 because these ones we can actually solve for, right? We have mass, we know that gravity's acting on them, we can figure out those values, right? This is part of the questions we're being asked to find, so if we don't have this as our pivot point, well, then we're kind of in a trickier spot, right? So this is our pivot point. right here. That's what we're choosing, right? So all of our forces that are acting on this, it's going to be, perpendicular to that line, okay? So again, each of our torques come from each of our forces, right? So we have 1, 2, 3, 4, 5 different torques that we're dealing with. So let's have it. So we've got the torque of the force of the wall in the x. Let's get rid of the f. Okay, so we've got the torque for the wall in the x, and the torque of the wall in the y, and the torque of the gravity, right? Or so the torque of the rod plus the torque of the sign plus the torque of the cable. Okay, all of that has to equal 0. Okay, so remember, torque being, right, length of the lever arm perpendicular to the force multiplied by the force. So, again, if we kind of actually wrote this all out, it's like, okay, well then this is going to have a value, right, multiplied by the force of Wx plus that length perpendicular times the force of the wall in the y plus that lever arm for the rod multiplied by the force of gravity of the rod, and then this value for the sign multiplied by the force of gravity of the sign, and then the distance for the cable multiplied by the force of the cable, which is the force of tension. All right, so looking at this, right, we're going to need to figure out some values. Ultimately, this is what we want, right? Force of tension is what we want. And if we go through it, it's like, okay, well, from the distance from the pivot point, that's 0, so this whole thing becomes 0. Great, right? For force in the y, right? Force of the wall in the y. Again, distance here from the pivot point, 0. Great, that's gone. All right, let's talk about here. The distance of the lever arm for the rod. Well, that's already nice and perpendicular to the force that's acting on it. So we just need to know, what is this distance? Well, in the question, it told us that the length of the rod was 1.3 meters. So all we need to do is cut that in half, right? So the length of the rod was 1.3 meters. So if we cut that in half, that means that distance for the lever arm is going to be 0.65 meters. So for this, we get the 0.65 meters. And to get our force of gravity, it's our mass of the rod, which is our 7.8 kilograms, multiplied by our force of gravity. And that's going to be acting in a negative, so negative 9.81 meters per second squared, right? Now for the sign, it's hanging symmetrically, so it's the same value, right, for this distance from the lever arm, right? So that's going to also be 0.65 meters multiplied by our force of gravity, which is again our mass of 18 kilograms, multiplied by our negative 9.81 meters per second squared. And then here, this is what we're still trying to figure out, right? So I'll just leave that for a second. Okay, and that's all equal to 0. And I'm going to just redo this now in a second so we get that looking a little bit better. So ultimately, we can multiply all this to get the torque of the rod. We can multiply all this together to get the torque of the sign, and then that allows us to solve for the torque in the cable, which will help us. Okay, so let's kind of go back to what we have then. Okay, so again, if you actually did all that math out, right, so the zeros are gone, and then we find out what is that 0.65 times 7.8 times 9.81, right? You get a value there of negative 49.7367 Newton meters, and then the other one ends up being negative 114.777 Newton meters, and then it was, like we said, plus that the cable multiplied by the force of tension equaling 0. So this is what we want to deal with. So let's subtract these from both sides, so we end up getting the following. All right, so you can kind of add these together and then bring them over, and you get a value of 164.5137 Newton meters. Okay, now this is what we want, so can we figure this out, right? And the answer is yes. Okay, so what we're looking for is that distance that's from the distance from the pivot point that's perpendicular to the force of tension. So here's my force of tension. How do I draw that perpendicular line to the pivot point? Like this. Right? And there's my distance of our lever arm that we need. Right? And again, we create this wonderful little right angle triangle, right? Where we know that the length here of the rod, that whole length there was 1.3 meters. So what we're looking for is the opposite side length there. So we're looking for sine, right? So that value is going to come from sine of 35 degrees multiplied by the 1.3 meters, and then that multiplied by your force of tension is equal to our 164.5137 Newton meters. So then all we need to do is multiply this together and then divide. Okay, so then what we get is when we multiply this, we get 0.7456 meters times our force of tension is equal to that 164.5137 Newton meters. And then we'll just take this 164.5137 Newton meters, divide it by the 0.7456 meters. You'll notice that the meters will cancel and you'll just be left with a force of tension in the cable, which ends up being like 220.63 newtons. And I think we get 2 sig figs, so 2.2 times 10 squared newtons. And of course we know that it's at an angle of 35 degrees, right? So you can see the force of tension is 2.2 times 10 squared newtons, 35 degrees from the x-axis, or west, 35 degrees north, however you want to say it. Okay, so there's A, right? Not so bad as the last problem that took forever. So we just had to use the torque in that case. Okay, part B is asking what's our force that the wall exerts on the sign, and like I said, there's 2 components of that. So we now need to look at, okay, well I got to figure out what's the force of the wall in the x, what's the force of the wall in the y, and then combine them together using vector components to be able to get the overall force. So let's do that. Because now, what's nice is if we look at the sum of the forces in the x, right? We know, again, it's in equilibrium, so it's going to equal 0. So in the x, don't need to worry about this. This is only happening in the y. Don't need to worry about this. It's only happening in the y. Also only happening in the y. We only actually have 2 things happening in the x. You have the force of the wall in the x, and you have the x component of the force of tension. Okay? Now, you knew, or we calculated in part A, that the force of tension was that 220.63 newtons. I'm going back to its exact value to get a value there. And the x component there, right, using that 35-degree angle, is here, right? So if we kind of think about this diagram here, this being the force of tension of 220.63 newtons, you have force of tension in the x here, and then you've got your force of tension in the y, right? And because you know that this is a 35-degree angle, we can find this value just by using some right angle trig, right? And because it's the adjacent, it's the cosine, right? So our force of tension in the x is just going to be cosine of 35 degrees multiplied by the 220.63 newtons, okay? So force of tension in the x ends up being a value of, where did I write that down? Oh, 180.73 newtons. And actually, if we look at it, it's actually acting to the left, so this will have a negative value, right? So there's our force of tension in the x. So now, going back to this, knowing that the sum of those 2 things, that should be an x, not a w. Okay, the sum of those 2 x components has to equal 0. I'm interested in this. So the force of the wall in the x is equal to the negative force of tension in the x. So make that negative negative. So the force of the wall in the x will end up being a positive 180.73 newtons. Wonderful. Right? Now we do the same thing for the sum of the forces in the y. That also needs to equal 0. Okay? So I'm actually going to put that back up here. Right? right? So the sum of our forces in the y also needs to be 0. So in this case, we've got a few other things going on, right? You've got the force of gravity of the rod, you've got the force of gravity of the sign, you've got the force of the force of the wall in the y, and you've got the force of tension in the y, all equaling 0. Okay, so ultimately this is what we're trying to find. So the force, the wall in the y will equal, well, these force of gravity would have been acting in a negative direction, so you can kind of think of them as these are negative values, whereas this was positive and so was this. So when we bring these over, they become positive. And then when we bring this over, it becomes negative. Okay, so your force of gravity of the rod, again, is just going to be its mass, which was 7.8 kilograms multiplied by your 9.81 meters per second squared. Right, so if we kind of do this, so that's our, no, that was 7.8 for the rod. The sign is 18, right? So that's 7.8 multiplied by our 9.81. It's now positive because we brought it over, okay? Plus the force of gravity of the sign, which was 18 kilograms multiplied by our 9.81 meters per second squared. Now our force of tension in the y, right, again comes back to this diagram here, where you'd now be looking for the opposite side length, so you'd use the sine of 35 degrees, right? So your force of tension in the y is now your sine of 35 degrees multiplied by your overall force of tension that we solved for in part A, which was the 220.63, and that gives you a value of 126.548 newtons, right? So that value then gets subtracted here. Right, so that would be a kilograms multiplied by your acceleration, so newtons, newtons, newtons. So your force of the wall in the y, this ends up being, so 76.518 newtons plus 176.58 newtons, and then minus the 126.548 newtons. So altogether, your force of the wall in the y direction is 126.55 newtons. Okay, so now you have the force of the wall in the y, we solve for the force of the wall in the x, so we put it together to just figure out what's the overall force of the wall, and we do that using vector components. Right, so again, basically what's happening is you've got, right, force of the wall in the x, force of the wall in the y, and that solves for overall a resultant. This is the force that the wall exerts on the sign, right? So this had a value of the 180.73 newtons. This had a value of the 126.55 newtons. So our force of the wall is just found using Pythagorean theorem. So the square root of the sum of these things squared. And the force that the wall exerts on the sign is 220.63 newtons, which actually comes down to, again, 2 sig figs, 2.2 times 10 squared newtons, again at that 35-degree angle. So it's kind of interesting that your force of tension in the cable actually ends up equaling the force that the wall exerts on the sign. I don't think that's true for all cases, but interesting in this particular case. Okay, so there was sample problem number 2. All right, let's take a look at sample problem number 3. So again, there's your solutions. Oh, I didn't actually solve for that angle, but it does end up equaling to 35 degrees. Right, again, it's just a matter of tan inverse, right, of those two values there. But again, because it was equal, you were going to get the same angle. Anyway, okay, so there we go. All right, so sample problem number 3. Here we go. So here we have the Morrissey Bridge, which is pictured above, will collapse if column A must support more than 5.00 times 10 to the 4 newtons of weight. The bridge spans 225 meters and has a mass of 8.5 times 10 cubed kilograms. Okay, that's the entire mass of the bridge. Will the bridge collapse under the circumstances? okay? And we're being asked to use 3 sig figs in our solution, right? So even though you can see here that the masses are given as just 500, 400, right, and these lengths are 75 and 50, we're still going to use the 3 sig figs here, okay? Okay, so thing that we're interested in is obviously finding, well, what, what weight is happening on this column, right? So if we can figure out, well, what's the weight that column A is supporting, and then compare it to this 5.00 times 10 to the 4, we can kind of get our solution that way, okay? So let's take a look at how we would kind of set this up in a simpler manner, okay? So what we've got is, again, our bridge, right? So we have column A here, we have column B here. We've got a car that's here with a force of gravity obviously acting on it, right? So force of gravity of the car. The bridge itself has a weight, so we have to cut right in the middle there, right? So this would be force of gravity of the bridge. Now that should obviously be a larger arrow because it's, right? So that's the force of gravity of the bridge. Right, I'm actually going to call that MB, like the Morrissey Bridge, force of gravity of the Morrissey Bridge. Okay, and then we have some other shape vehicle thing that I don't really know what it is. So I'm just going to call it force of gravity of, I don't know, quad. It's a quad. All right, so it's a cube. Okay, now we know that the length of the bridge this way, tire length of the bridge is 225 meters. We know that this distance between these two guys is 50 meters. We know that this distance here is 75 meters. The distance to here is going to be exactly half. So that would be 112.5 meters there. And we're actually interested in what's the force of column A, right? So what is, right, what force does column A have to support at this point? Okay, so these forces would be pulling it down, this one would be pulling it up. And again, obviously column B is supporting a force as well, but we're not interested in any of that, right? So again, this leads to this question of, well, where should I select my pivot point? I don't want to select my pivot point here at A, right? Because then that would mean that the distance, the lever arm from that force is going to be 0. It's not helpful, right? It won't allow us to solve for it, right? So again, what I should do is consider the bridge instead from pivot B, right? So this can be my pivot point over here. And then I do everything in relation to this point here. And this one ends up being a little bit nicer because we don't have as much, really any trig to deal with because it's all just happening on a flat, straight surface, okay? So if we start thinking about, what's happening with this, right? Again, if we start looking at, well, obviously, okay, so again, we've got forces all acting in the y's is really all that's happening, but we'll need the torques to kind of deal with that, right? Because I don't know this exact, because again, it's a bridge that could potentially do this, right? So we have that pivot point. So let's start by looking at torques for each of these, okay? So what I could do is, again, just break this up into little sections. So, I'm looking at, okay, let's start with the car, right? And the torque of the car is going to equal that distance of the lever arm multiplied by our force of gravity of the car. We know, since it's from the pivot point, though, we're not going to use the value of 50. We're just going to subtract 50 from 225 because this is now the distance from the pivot point. So 225 minus the 50 gives us 175. Right, so that's 175 meters multiplied by our force of gravity, and the car was given to us as 500 kilograms multiplied by our negative 9.81 meters per second squared. So the torque of the car ends up equaling a value of negative 85837.5 Newton meters, right? Negative again, because if we're, right, putting this here and then rotating in the force, it's going down, okay? Thumb's going into the page. So there's a torque of the car. We can do the same thing for the quad, right? So again, your torque of the quad is going to equal that distance of the lever arm multiplied by the force, and that's for the quad. Okay, so in this one, the distance of the quad is 75 meters multiplied by its mass of 400 kilograms multiplied by our acceleration due to gravity, 9.81 meters per second squared. So the torque for the quad ends up equaling negative 294,300 Newton meters. Okay, so there's the torque for the quad. Then what we've got, make that a little bit easier so there's less sunlight coming in. Okay, then we can look at torque for the actual bridge itself. Okay, so we can look at the bridge. Okay, so again, so the torque for the Morrissey bridge, again, all right, lever arm multiplied by the force, the bridge. So in that case, this distance from the pivot point to the center of mass, the bridge will be the 112.5 meters multiplied by the mass of the bridge, which was 8.50 times 10 cubed kilograms multiplied by our negative 9.81 meters per second squared. Okay, so the torque of our Morrissey bridge ends up equaling negative 9,380,812.5 Newton meters. And then finally, we have the torque of column A itself. Okay, so we got column A over here. Okay, so again, our torque of column A is that distance of the lever arm multiplied by the force. Okay, and now this one we can't fully solve, right? But then again, we do know that the sum of all the torques is going to equal to 0, so we will be able to figure this out. So we know the distance from the pivot point is the 225, right? So that's 225 meters multiplied by the force of column A, which is what we're going to solve for. Okay, so just keep that in mind. So now, the sum of all of our torques is going to equal 0. So, sum of the torques need to be 0. And all of our torques, we've got the torque from column A, the torque of the car, so C, we've got the torque of the bridge, we've got the torque of the quad, and all that is 0. Okay? So we found values for all of these, all acting in a negative direction, so when we actually bring them all over, they'll be positive because they'll be subtracting negatives and will turn into positive. So our torque for the column A will end up equaling so this would be 85,835 Newton meters plus the 29,4300 Newton meters, and then plus that like 9,180,812.5 Newton meters. Okay, and again, remember your torque for A was equal to this 225 meters multiplied by your force that column A is dealing with, which ends up equaling 0.53347.5 Newton meters. So to solve for that force, we just need to divide both sides by the 225. And when we do that, we get a value of 46,815.5 newtons, which, if we're thinking 3 sig figs, is going to be 4.68 times 10 to the 4 newtons. And if you look at the question, it said that the maximum it can support without it collapsing is 5.00 times 10 to the 4 newtons, which is less, so we're not going to collapse in this case. Okay, so there we go. Okay, so that's the force that it's supporting at that point, and we're able to figure that out. So that was perfect. Okay, so again, using that equilibrium. So we got one last example, sorry, to try and take a look at. Okay, so again, you see all that work there, right? So this one is done in a way where you're actually just setting it all up in the one formula, right? I kind of broke it down to show you finding each of the torques and then setting it up, but you can do it all in just that one nice step. Okay, so finally we look at example 4, right? Very, very common type of question about, two cables support a mass, and you're wondering, well, what's the tension in each of the cables, right? So this one might be a little bit more familiar to you, but we'll take a look at it. Okay, so again, the idea here in this one, though, is we don't actually really need torque. It's just a matter of equilibrium, right? Because we can figure out what's going on with each of the tensions in the x component and the y component, and then set our sum of our x components and sum of our y components equal to 0, and go from there. All right, so just as a refresher, I think you may have seen these ones in Physics 11, but just to kind of show you examples that don't always have to use the torque value. All right, so this was that diagram for number 4. Okay, 2 walls. They're at different angles, right? So you've got one that's doing this. You've got this mass, right? There's your weight of 100 kilograms, and then this one is attached further up, right? And they're at different horizontals, right? And it tells us in the question that one makes a 35-degree angle with the horizontal, and then the other one makes a 42-degree angle with the horizontal. So this is our tension 1, and then this is our tension 2, right? So again, if we're at equilibrium, that means that the sum of all the forces in the x is 0, and the sum of all the forces acting in the y are equal to 0. All right? Now, what I can do is actually kind of set up a system of equations in this one, right? So what's happening here is that we don't know the force of tension in either one of these cables. However, we do have that there's a force of gravity acting on this particular mass, right? So there's a force of gravity acting on the mass. We can find that, right? So the force of gravity on that particular mass is it's 100 kilograms multiplied by our negative 9.81 meters per second squared. So the force of gravity there is just equal to negative 981 newtons. Okay, so like I said, our sum of the forces in the x have to equal 0. There's no x component to this force here. There's only x components to each of these tensions. So our force of our x components, right, being 0, are just, well, there's the x component of the first cable, right, so T1x, and then there's the x component of the second cable, right, so force of tension in the second cable x, those are going to equal 0. Okay, now we don't know either of these right now, but we could kind of figure out what they would be, because if we looked at this as like a right triangle here, right, this is the overall force of tension in one, which is what we're trying to find, and the force of tension in the x would end up equaling the cosine of that 35 degrees. So while we don't know the actual value, we can at least set this up to be cosine of 35 degrees times the force of tension 1, times the force of tension 1. Okay, that's what will happen there. Okay, and this would be acting in this direction, so we'll call that a negative. All right, same thing can happen here for the x, right? This would be that tension in the x for 2, and then again would be the cosine of 42 degrees multiplied by that, which would be our hypotenuse of T2. So this would be plus cosine of 42 degrees multiplied by T2 equaling 0. Okay, now that equation is going to be really important because we're going to use it when we set up our next thing. Okay, so I'm going to try and leave it there, see if I have space. All right, so I might just erase this a little bit for now. So that's what we have for force of sum of the forces in the x. We can also then look at our sum of the forces in the y, which we know we've got 3, right? So again, you've got the y component of the force of tension in the first cable. You've also got the y component in the force of tension of the second cable, and then you've got your force of gravity of the actual mass. So what you have there is, okay, so force of tension of the first one, force of tension in the second one, and then your force of gravity, all adding to 0. You have a value for this, We don't have values for these, but they are related to T1 and T2, which in this case would be the sign values, right? And these actual tensions are pulling up. So I drew those vectors wrong because the cable is pulling up on the mass, and this would be negative, right? So this value here is going to use the sine of 35 degrees times whatever that hypotenuse force of tension in the first one is. This one will use the sine of 42 degrees to find this value because it's opposite, right? Sine of 42 degrees multiplied by a force of tension in the second one. And then that will equal, so if we bring this negative 981 over, a positive 981 newtons. Okay, so again, we don't know T1, we don't know T2, but now we actually have two equations, right? So now we kind of set this up as like a system of equations, right? Solving by substitution or elimination. So what we could do from this one here is, let's say we get T2 by itself, right? So we bring this entire term over, and it becomes positive, right? So then what we get is that this cosine of 42 degrees multiplied by T2 is equal to the positive cos of 35 degrees times T1, and then to get T2 by itself, we divide both sides by cos of 42. So T2 now is equal to cos of 35 multiplied by T1, all divided by cos of 42. And I mean, these are constant values. You can get decimal approximations here, right? And then this whole thing gets substituted in here for T2. So then what you end up having is, by substituting this into here, we get this idea of sine 35 T1 plus sine of 42 multiplied by cos of 35 T1 divided by cos of 42, all equals 981 newtons. Okay, so then like I said, these can just be calculated on a calculator to give you like a decimal approximation here, and now your only variable is T1, so this ends up giving us like 0.5736 T1 plus, so if you do sine of 42 multiplied by cos of 35 divided by cos of 42, you end up getting a value there of 0.7376 T1 is equal to the 981 newtons. Now these are the same force of tensions, so we can add these two values together. So we get 1.3112 T1 is equal to the 981 newtons. Solve for T1, take your 981, divide it by your 1.3112. So the force of tension in the first cable is in fact 748 newtons, and we already knew that it was 35 degrees from the horizontal, right? So there's T1, and then in order to get T2, you're just plugging that value of T1 into this equation here, right? So cos of 35 degrees times that 748, and then divide by cos of 42. And then that value, right, okay, so like I said, that T2 is now the cos of 35 multiplied by the 748 divided by the cos of 42. And our force of tension in the second cable ends up being 825 newtons, again, 42 degrees from the horizontal. Okay, so that one didn't really need to use any torque in that case, but it did need some extra math of solving by substitution. And, well, you could have done elimination too, I guess, but there you go. Okay, so there's that second video with all of those sample problems done out, trying to with the explanation, and then you can kind of work on that, some questions on your own with the worksheet. Okay, there you go.